So this is the final topic in chapter 4, gas laws. So final topic in chapter 4. Then after that we have chapter 2 more chapters after this, which we should be on track to finish by the end of the year. So the three main topics that we will be discussing when we're talking about gas laws will be these things. We'll be looking at pressure, temperature, and volume of gas. So before I continue, I just want to remind you that none of these things that we are looking at here today are actually new, or at least most of it is not new. We will look into about 3 formulas today, but the idea of pressure, temperature, and volume of gas being related is something that you first studied way back in Form 2, actually. And if I remember correctly, yeah, you studied way back in Form 2 about gas, about how if you learn things like if you increase the temperature of a gas with the same amount of volume, you'll increase the temperature. Or if you keep the same mass of gas but you squeeze it so that it's in a smaller volume or smaller container, you also increase the pressure. So this is nothing new actually. It's just that now we're going to go a little bit more in depth into the calculations and a little bit on the mathematics. None of the calculations are very difficult, so I don't think you have to be worried about that at all. But these are actually things that you already have studied before this. So let's talk about this. Pressure, temperature, and volume of gas. So if you've ever bought anything from Shopee or Lazada, sometimes you know that when you get the box that has your items in it, you might find something that looks like this. You might find something that looks like basically a piece of plastic filled with air. So that's basically an air cushion wrap. And or sometimes it doesn't look like that, but I'm sure you've all seen bubble wrap. You know those little pieces of plastic with air bubbles, and everybody likes to get those and just pop each and every one of those bubbles one by one. Yes, exactly, Manuel. Very satisfying. People love to do that. And I'm sure all of you notice that when you pop those bubbles one by one, it doesn't just collapse. When you press those bubbles, you can feel as if the bubble is pushing back, right? It's the same thing with this air cushion. When you squeeze it, you can feel that the air inside is pushing back. Or maybe not necessarily this, but like if you have a bag of chips, or a bag of any other snacks, and you try to squeeze the snacks, you can feel the air inside pushing back. Right? So this observation, according to our textbooks, well, first of all, why do we put those air cushions? Obviously, we put those cushions to, protect the things that you've packaged in the box. You sent the things over hundreds of kilometers. It would be a shame if they showed up in your customer's house and you open the box and all the things inside are broken. So we use these air bubbles or air pockets to, protect it. However, back to what I was saying. When you squeeze it, you can feel that the air is pushing back. And so this observation can be explained in terms of behavior of gas molecules based on the kinetic theory of gas. And again, this is not something new. You have learned about the kinetic theory of gas way back in Form 2. So what is the kinetic theory of gas? Well, we'll look into that more and more as we go through this topic. Right, so this is basically a summary. You can find this in your textbook, but this is a summary of how the kinetic theory works. So there are 3 characteristics of gas that we'll be talking about, like I said. Talking about pressure, talking about temperature, and talking about volume. And let's just go through the description and let's see what this is basically a review of what we've learned in Form 2. So let's see. Pressure. So what is pressure? If you remember correctly, pressure is unit of force per area, right? We're talking about pressure, how much force over how much area. That's basically the simplest definition of pressure. So we know that gas molecules always moves randomly, right? It's not like a solid where the molecules are fixed, but they vibrate in a fixed location. In a gas, all the molecules are free to move in any direction, and any direction. And we also remember that when gas molecules collide with the wall of the container and rebound, a force is exerted on the wall of the container. So imagine those molecules moving around. Because they're moving around at random, they usually end up hitting the walls of the container, whatever container that you have for the gas that you have, be it a balloon or a gas tank or a any other kind of container that you have for this air, or not air but gas. And so when these molecules hit the wall of the container, that hitting causes a force to be exerted on the wall of the container. Now, one molecule by itself obviously does not give a lot of force, but remember there are probably millions of molecules, and each of these molecules are hitting the walls thousands or even millions of times per second. So because there are so many molecules and the collisions are happening so much, it's enough that there is a force that you can actually feel on the wall of the container. And that force is what we call the pressure of the gas. Force specifically per unit area. So how much force is being applied per square meter? That is what we call pressure. This is all a review of what you've learned in Form 2. Right? So the reason why pressure exists is because of these gas molecules moving around. Temperature. All right, so next thing, temperature. So average kinetic energy of gas molecules increases with temperature. So the more temperature, or basically the higher the temperature of the gas molecules, the more these molecules start to move, right? So they're always moving, but when you increase the temperature, they move even more. If you think about it, it makes sense. Heat is a form of energy, correct? So of course, the more heat you give, the more heat or the more energy you give to the gas molecules, the more energy these molecules now have to move. So the more you increase the temperature, the more you increase the kinetic energy, the more these molecules start to move. Now finally, we can talk about volume. Right? So gas molecules move freely again, and they fill the entire space of the container. So if you have a certain number of molecules, if you put it in a small container, then those molecules will just move around in the small container. If you put it in a bigger container, but you put in the same number of molecules or the same mass of gas, because gas can move freely, it can still fill up the entire container. So you can either have a smaller container and the molecules will have less room to move, or you can make a bigger container, same amount of gas, but because the gas can move freely, it can still fill up the entire container. Volume of the gas is the same as the volume of its container. So what I was just saying, you give it a small container, the gas will fill up a small volume. You give it a bigger container, the gas will fill up a bigger container, even though it's the same mass or same number of molecules. Now, when you read these three things together carefully, you start to understand how these three things actually are related to one another, right? For example, and this is still something that we learned already in Form 2. For example, pressure. Pressure is caused by what? When gas molecules collide with the wall. That's what causes the pressure. These collisions. Now, increasing the temperature increases how much these gas molecules move. More temperature, more heat means more energy. These molecules move faster and faster and faster and faster. All right. Now, Now that you know these two things, you can imagine what would happen if you increase the temperature of a gas. What would happen to the pressure? If pressure is caused by gas molecules colliding with the wall or hitting the wall, and increasing the temperature causes the gas molecules to move faster, then if I increase the temperature, what would it happen to the pressure? What do you think? Excuse me. So if you think about it, the more the gas molecules move, the faster they move, the more they collide or the more it hits the wall of the container. Therefore, it causes the pressure to go up. Right? The more you collide with the wall, the more there's pressure. And since temperature causes the gas to move faster, it causes the collisions to happen more often. The pressure also increases. So here you can see now that there is a relationship between these two. Okay, what about volume? Same idea. All right, if we take 50, let's say 50 molecules and put it in a larger container, right? Then these 50 molecules have space to move around in this larger container. If we take the same 50 molecules and now we force them into a smaller container, now they have less space to move. What happens? Less space to move means those gas molecules are more likely to what? Collide with the wall more often. And so what happens to pressure? Again, it goes up. So as you can see, all these things are actually related to one another, which you actually already learned way back in Form 2, right? So that's that. We're still only just reviewing what you already know from Form 2, but I hope you're already getting the idea that these three things are all related to one another. And the gas laws that we're studying today, we're just studying the relationship between all these things. That's all the gas laws are. What are the relationship between the pressure, the temperature, and the volume of gas? Okay. Now, before we continue, just keep this in mind. We have different units that we use for studying pressure, temperature, and volume of gas. So pressure, or sometimes we use the capital letter P. We use the SI unit Pascal, or Pascal, I believe, is newtons per square meter, if I'm not mistaken. Or we use the symbol PA, which means the same thing, Pascal. Temperature. Okay, here's an interesting one. Temperature. So normally we are used to calculating temperature based on Celsius. But for gas, we usually use Kelvin. I'll explain to you why later on in this topic. So we usually measure using Kelvin. And the symbol for Kelvin is just letter K. And volume, we use cubic meter or, cubic meter. Excuse me. So of course, we have other units that we use. For example, pressure. Sometimes we use centimeters of mercury. Okay, sometimes for temperature, we use Celsius, which we use quite often. Fahrenheit, we don't really use that much, but it's another unit that we use. And of course, cubic millimeter, cubic centimeter, and also milliliter. But for the purposes of this chapter, we will be mostly using these ones, right? The standard units. All right, so let's talk about the relationship between these things. So let's check the first one. Relationship between between pressure and volume of gas. So when I say relationship, remember, when I say relationship, basically what we're saying is, if I change one, for example, if I change the pressure of the gas, or if I change the volume of a gas, how does that affect the pressure? That's what we mean when I say relationship. So photograph 4.4 shows an exercise ball. I'm sure a lot of you have tried sitting on one of these exercise balls, and when you sit on it, it compresses. So what happens to the air pressure inside the ball? Does the air pressure inside the ball go up or down? Because when you squeeze the ball, right, you have the same amount of air inside, but when you squeeze it, what you're doing to the volume is you're basically making the volume smaller. So easy way to do it, use a graph. So if we take a look at a graph, let me remove my face that's blocking, sorry. Relationship between pressure and volume of gas. So if we take a look at the first graph here on the left. So graph P for pressure against V. So V for volume. Now what you can see here is this. The more you increase the volume, what happens to the pressure? The more you increase the volume, the more the pressure goes down. Right? That's what this graph means. Or if you go in the opposite direction, the more you decrease the volume, the more the volume gets closer and closer to zero, what happens to pressure? Pressure starts to go up or pressure starts to increase. All right? Or we can also do it like this. We have P and we have 1 over V. So this is the graph on the right side. So if we make a graph of P against 1 over V, you see that it is a straight line going through the origin or going through 0. So basically, in short, what we're saying is, if we have these two, we have pressure and volume, and we assume that mass and temperature stays the same, okay? The more the volume goes up, pressure goes down. Okay? If you increase volume, pressure goes down. If you decrease the volume, meaning to say you make the container smaller, what happens to pressure? Pressure goes up. So what do you call that relationship? When one goes up, the other goes down, or the opposite? We have a word for that relationship. We say that, okay, we say that pressure is inversely proportional to volume, meaning to say, when we say inversely proportional, meaning to say when one goes up, the other goes down. All right, so Boyle's law states that pressure is inversely proportional to volume for fixed mass of gas at constant temperature. Now, of course, you cannot ignore these two things. Fixed mass of gas, right? So, and constant temperature. So Boyle's law is assuming that, one, the gas does not change temperature, because if you change the temperature, then it also changes the pressure and also changes the volume. And fixed mass of gas, of course, the mass of the gas, the number of molecules is the same, right? So if these two are fixed or does not change, then pressure is inversely proportional to volume, meaning to say, if we assume that the temperature and the mass is the same, then when volume goes up, pressure goes down. If volume goes down, pressure goes up. That's Boyle's law. An easy way for you to understand is by looking at this picture, right? You see that the number of molecules remain the same. But when you make the container, when you decrease the volume, make it smaller, what happens? Now that the molecules have less space, it collides with the walls more often, therefore you get a higher pressure. And the opposite is also true. When you increase the volume, you give it more space, you use a bigger container, same number of molecules now have more space, so less likely to collide with the walls, therefore lower pressure. So this is a good picture to help us see it. And by the way, these pictures are all in your textbook, so you can also take a look in your textbooks later. Okay? So this is the formula that we can usually use. So P is inversely proportional to 1 over V. Or if we write it, so pressure equals K 1 over V. K being the constant. So K is a constant, P is gas pressure in Pascal, and V is gas volume in square meter. And as such, if we were to rearrange the formula, we have PV equals K, obviously, because let me see if I can get that. So, because obviously, if we were to rewrite the formula, P equals K, 1 over V. If we were just to rearrange the formula, move the V up, we can move this here. So P equals PV equals K. Quite a simple calculation or simple way to write the formula. And so the application here is this. If a gas experiences a change in pressure and volume from condition 1 to condition 2. Meaning to say, just so that you understand, let's say we have a certain amount of gas, let's say in a balloon. And this balloon is this big and there's this much gas inside. Let's consider this condition 1. Alright? Now, when we go to condition 2, now let's take the balloon and squeeze it to a smaller size. Let's call that condition 2, or the second state. So since in both situations we have the same mass of gas, meaning same number of molecules, and same temperature, the only thing that changes is the pressure and volume. Okay? So since it's the same since it's the same mass and temperature for both situations, we can assume that PV for the first situation equals PV for the second situation. Therefore, PV1 equals PV2. We'll take a look at the example question right after this. So here's an example question. So let's read it first. So air in a closed syringe has a volume of 60 centimeters cube and pressure of 108 kilopascals. The piston of the syringe is pushed to compress the air to a volume of 48 centimeters cube. So calculate the pressure of the compressed air. So what we have here is a situation where you give this gas two different conditions. Condition 1 is 60 cm of volume, cm cube of volume, and 108 kilopascals. The second situation, you're given the volume, but you're not given the pressure, right? But since we know that we're talking about the same mass of air, then we can use the formula that we were just reading just now. So let's take a look at the information that we have. So let's see. So P, pressure in the beginning, or P1, according to the question, actually let's put it like that. So according to the question is 108 kilopascals. And go ahead and follow along with your calculators, yeah? Okay. Pressure for the second state or after you change the volume is not given. And that is what the question is asking for. Okay, volume in the beginning, 1 equals 60 cubic centimeters. And volume at the end is 48 cubic centimeters. All right. Now we have to assume it's not stated in the question, but to help us solve the question, kita anggap sajalah, assume that temperature is the same. We assume that the temperature is the same, and we will use the formula that we were just looking at earlier. So what was the formula that we just looking earlier? We can use this one. So we know that P1, so this is before you change the volume and after you change the volume at the end. So once you got all of that, then it's just a matter of writing down all the information. So let's write it down. So 108 times 60 equals P2 times 48. So P2, if we were just to rewrite everything, equals 108 times 60 divided by 48. All right, and your final answer is, can someone calculate that? It's in your textbooks, come on. You don't need to calculate that. 135. Yes, exactly. So 135 kilopascals. All right. So that is Boyle's law. Uh, basically, it's basically mostly most of the equations in this chapter is basically in mathematics you'd call it simultaneous equations. Simultaneous equations, very useful in physics. Yeah. All right. So that's basically how it is. All right, let's continue. So, Boyle's law. So, just remember Boyle's law. When we're talking about Boyle's law, we're talking about volume and pressure, the relationship between these two things. All right, let's continue. So, now let's look at the relationship between volume and temperature of gas. So, photograph 4.5 shows an empty plastic bottle filled with air in a refrigerator. What happened to the volume of air in the bottle? So if you can do this experiment at home, right? Take an empty bottle, fill it with nothing. Close it so that it's full of air, and then put it in the fridge. And as you can see in the picture, before it gets cold, it looks like it's full. But when you cool it down, the bottle starts to compress. In other words, the volume of air inside the bottle actually starts to get smaller. So what happens? So if we were to make a graph, all right, if we were to make a graph in Celsius, okay, so this is an example of a graph that you plot. So you take different temperatures and you measure the different volumes. So that's why there are those little X's over there. Now, if you connect all the little dots, you create a straight line. And by using extrapolation, meaning to say, continuing the straight line all the way down, you find that the relationship in theory, remember this is just in theory, the lower the temperature, the lower the volume. So you see it's a graph of V of V against the temperature. So you see, the higher the temperature, the higher the volume. The lower the temperature, as you go lower and lower and lower and lower, the volume also gets lower and lower until theoretically, most scientists agree theoretically that at around negative 273, the volume also becomes zero. So at a temperature of negative 273, theoretically, gas molecules no longer move. So what happens is, we know that molecules are moving, and because they are moving, they create pressure and create space or volume. Now, when you add more temperature or add more heat, it gets more energy, it moves more and moves faster. The opposite is also true. If you reduce the heat, meaning to say you reduce the amount of energy available for these gas molecules, they start to move smaller and slower. And by continuing that logic, if we go all the way down to negative 273, we reach a point where these molecules no longer move. There's no energy for it to move, and it does not fill any space, and such the volume of the gas becomes zero. So this temperature of negative 273 degrees Celsius is theoretically, I should emphasize the word theoretically, the lowest temperature possible. There is no such thing as lower than 273. Again, like I said, theoretically. And that's why we call this absolute zero. So absolute zero means there's no heat, there's no energy left. So because of this, scientists have come up with a different scale. Instead of Celsius, we use a scale called Kelvin, where this point of absolute zero, we really call it zero. Therefore, temperature that is stated in unit Kelvin is absolute temperature. So the reason why we call it absolute temperature. Now, normally when we calculate temperature, we either use, well, here in Malaysia, most commonly we use Celsius. However, when the thing about Celsius is it's not an absolute scale. What I mean is when you reach zero, it doesn't mean that the heat is zero. We just use zero. We use the freezing point of water as zero, but you can actually still go colder, right? You can still go to -10, -20, negative whatever, right? Because it's still possible to go colder. It's still possible to take away more heat. Now, the idea of the Kelvin scale is that absolute zero is really zero. There's no such thing as negative Kelvin, because in theory negative Kelvin does not exist, because there's no such thing as negative. Well, there is such a thing, but in this situation, you cannot say negative energy. You understand what I'm saying? Absolute zero means there's no more heat, there's no more energy, and you cannot take away any more energy. So zero. So that's why there's no such thing as negative Kelvin. So that's why we call it absolute temperature. Because when I say 0 Kelvin, it means it really starts from zero. Unlike other types of calculations, like what does I say? Like Celsius, zero Celsius, you can still continue to go colder. 0 Fahrenheit, you can still continue to go colder. 0 Kelvin, no, you cannot go colder than that. All right, so temperature. So if we were to convert it, right, we'll just compare. So absolute zero, that's the same as negative 273. But if in Kelvin, it will be 200. All right. How about ice, melting ice or freezing point of ice? In Celsius, it would be 0. In Kelvin, we would say 273 Kelvin. What about boiling water? Okay, 100 degrees Celsius, that's the same as temperature in Kelvin would be 373 Kelvin. Now, the good thing about Kelvin is it's very easy to convert. It's very easy to convert Celsius to Kelvin. Just remember this. Okay, so conversion of units between Celsius and Kelvin can be done using the following equation. T equals, that's basically an omega sign. So T equals omega plus 273. All right. So to get the number in Kelvin, to convert Celsius to Kelvin, you just add 273. Exactly, Emmanuel. Or if you want to do the opposite, to find Celsius from Kelvin, you just take Kelvin and minus 273. So it's a good thing. It's not too difficult. You just need to. It's just a different starting point. Now, if you want to change to Fahrenheit, then that's a little bit more complicated. But luckily, we don't have to. We're not using Fahrenheit, so we won't go into that. So you need to remember this, because a lot of the calculations that we will be studying, you need to convert Celsius into Kelvin. Now, this is actually the same graph, but now instead of using Celsius to cubic centimeters, we're using Kelvin to cubic centimeters. It's the same graph, okay? So graph of V against T for a gas, right? You can see the relationship. You have a straight line that goes through the point of origin. So this shows that the volume of gas is directly proportional to absolute temperature. Meaning to say, as the temperature goes up, the pressure also goes, as the temperature goes up, the volume also goes up. Okay. This is assuming that the mass and the pressure does not change. So if the pressure does not change and the mass does not change, then when volume goes up, temperature also goes up. When volume goes down, temperature also goes down. And vice versa. So remember the hot air balloon that we are talking about, that they were talking about in the video in the beginning. When you heat up air, when you heat up air, what happens to the air? The air starts to increase in volume. It starts to expand because it's getting hotter. Now what happens to the density when the volume increases? Density also starts to go down, right? Because density is mass divided by volume. And so because the hot air is less dense than the cold air outside, the balloon starts to float or go higher. That's how a hot air balloon works. So for this law, we have a different person now. We call this Charles' law. So, Charles' law states that volume is directly proportional to absolute temperature, like we just said, for a fixed mass at a constant pressure. So, the thing that is fixed here is mass and pressure. So, if we will take the formula, we have V is proportional to T. So, V equals KT. So V equals KT. So, K is a constant. T is absolute temperature. So we are usually going to use absolute temperature or Kelvin for our calculations. V is volume of gas in square meters. And since V equals KT, sorry, it should be capital letter T. Since V equals KT, we can easily rearrange the formula to mean that V over T equals K. And just like the equation just now, again, same idea. If a gas experiences a change in volume and temperature from condition 1 to condition 2. So same idea. Same amount of gas and same pressure, but now we have two different situations where the temperature or volume changes. All right? Then situation 1 or condition 1 is going to equal condition 2. So V1 over T1 equals V2 over T2. Condition 1 should equal condition 2. So here is another picture. I really like the pictures that they use for this one. So fixed mass of gas heated at constant pressure. So what happens? When you increase the temperature, what happens? Remember, the gas starts to move faster. And so in order to keep the same pressure, you have to give it a larger volume so that the pressure remains the same. Because remember, more temperature, more heat means the molecules can move around faster and move further. So the volume automatically increases. All right, let's do another question. An air bubble of volume 1.2 centimeters at a temperature of 27 Celsius. What is the temperature? What is the volume of the air bubble if its temperature increases to 47 degrees Celsius? Okay, same idea. Okay, just a different formula. So this time we'll be using this formula here. All right, so let's take a look at our information. So what's our information? Okay, volume in the beginning, it's 1.2. Volume in the end, not stated. That's what we need to calculate. I should write down the unit as well. All right, now temperature. Okay, temperature in the beginning is 27 degrees Celsius. Now remember, we want to change it to Kelvin, so we have to add 273. So you will get a total of 300 Kelvin. So this is the temperature, initial temperature. And final temperature is 47. So 47 degrees Celsius, converting it into Kelvin, you get a total of 320 Kelvin. So remember, for the gas laws, you have to use Kelvin. Now, let's take a look at which formula we're going to use. So we're going to be using this formula. So we'll write down the formula as well. So V1 over T1 equals V2 over T2. And again, simply put, we'll just continue the formula. You can also follow along. So V1 is 1.2 over T1 equals 300. V2 is not stated, so we'll just use V2. T2 is 320 Kelvin. Rearrange the formula, so V2 equals 100. There are different ways you can write it. You could write it like this. The textbook writes it like this. Over 300. Alright. So basically, and if you follow along in the textbook, calculation is 1.28 cm cube. And that is your final answer. So the final volume after increasing the temperature is 1.28 square centimeters. So Boyle's law and Charles' law, basically all the laws that we're looking today are almost the same. The application of the formulas are almost the same. We're just looking at different relationships. And that's really the most important thing for you to understand. Besides learning how to use a formula, the other important thing for you to understand is how these relationships work. How does changing one aspect of the gas change the other aspects of the gas? Okay, one last formula or one last relationship to take a look at, which is the relationship between pressure and temperature of gas. So how does changing the pressure or how does changing the temperature affect the overall pressure? So photograph 4.6 shows air pressure in the tire of a car being measured on a hot day. The driver of the car touched the tire after the journey and found that the tire is hotter than before the journey. Obviously, if you're going to go drive, after you finish driving, the tires will be hotter due to hot weather and also friction. Photograph 4.7 shows the readings of the pressure gauge before and after the journey, what happened to the air pressure inside the tire. So you measure the air pressure. Now it's not very clear, right? But you can see that in A, before the journey, it's just slightly over 200. And at B, you can see that it's much more than, it's much more than 200. Looks more like 230. Right? If you can't see the picture clearly, go check your textbook or ask me for the picture later. I can send it to you. But what happens is, again, same idea. If we were to create a graph comparing the temperature and the pressure and create a straight line, and if we were to extrapolate all the way, you find that first you see that the more the temperature increases, the more the pressure also increases, assuming the volume remains the same. And as you go down, as you get colder and colder, pressure also gets lower and lower until you reach negative 273. Pressure also becomes 0. So once again, at absolute 0, gas molecules no longer move. Remember, since they no longer move, not only they do not have any volume, they also do not have any pressure. So gas pressure becomes 0. So this is a theoretical absolute 0. So again, if we were to make the graph, if we were to plot the graph of Kelvin against Pascal, you'd see straight line going through the point of origin. Therefore, according to this graph, what is the relationship? The relationship is that gas pressure is directly proportional to absolute temperature. So again, when temperature goes up, gas pressure also goes up. When temperature goes down, gas pressure also goes down by the same thing as well. If you make the gas pressure go up, then the absolute temperature is also going to go up or go down. So this time, finally, a different name. Okay, Gay-Lussac's law. I'm not sure if it's pronounced Gay-Lussac or Gay-Lussac or Guy-Lussac. It's a French name, and sometimes French have different ways of pronouncing it, right? But in some videos I check, it's Gay-Lussac. So Gay-Lussac's law states that pressure is directly proportional to absolute temperature of a fixed mass. So meaning to say the mass does not change and the volume does not change. Again, same idea. P is directly proportional to T, or absolute temperature. P equals KT. And again, same thing. If we were to rearrange the formula, P equals KT, rearrange the whole thing, then we get P over T equals K. We just move it over there. And exactly just like these other formula that we learned, if we take a gas and change the condition, okay, we change the temperature and the pressure, mass remains the same, volume remains the same, then since it's a constant, P1 over T1 should equal P2 over T2. Therefore, P1 over T1 equals P2 over T2. Alright, so here is the picture. So if you can see what happens here. If you keep the volume the same on both sides, you keep the mass or number of molecules on both sides the same. When you increase the temperature, what happens? The molecules move faster. Moves faster, moves further. And because it's in the same volume, in the same container, but it's moving faster, it's going to hit the walls more often. When it hits the walls more often, temperature goes up. Makes sense. So you give more energy, pressure goes up. Or you take away energy or reduce the temperature, pressure also goes down. Alright, last example for today. We're almost done. Well, at least we're almost done for lecture. You still have work to do after this. So gas in a closed steel cylinder has a pressure. So this is the last example for today. Has a pressure of 180 kilopascals at the temperature of 25 degrees Celsius. What is the gas pressure when the cylinder is heated to a temperature of 52 degrees Celsius? So again, same idea. Let's write down all the information that we already have. So let's start. What do we have here? First of all, pressure. So pressure in the beginning is 180. Pressure at the end, not stated. Temperature in the beginning, and remember we'll be using Kelvin. So 25 degrees Celsius, but to convert to Kelvin, we add 273. So temperature in the beginning is 298 Kelvin. Temperature at the end, or final temperature, 52 plus 273 equals 325 Kelvin. Okay, go back to the formula that we were just looking at. So P1 over T1 equals P2 over T2. And once you have all the information, same idea, just put all the information. It's all about finding the correct information, finding the correct formula, and then putting everything into place once you have everything. Right? So P1 equals 180. T1 equals 298 equals what? P2, not stated. That's what we need to find. And T2, or final temperature, is 325. So if we were to rearrange the formula, this is what you would get. You could also write it like this. You'd still get the same answer. And you get a total of 196.3 kilopascals. So those are all the three different formulas that you could possibly use. So there's Charles' law, there's Boyle's law, and there's Guy-Lussac's law. And so basically, you just have to remember which you just have to remember which law is talking about which aspect. So which one is talking about temperature and pressure, which one is talking about volume and temperature, and which one is talking about volume and pressure. Now there's another equation that combines all three, but you'll not be learning that today. That'll not be in Form 4, I think. I checked and it doesn't seem to be in your textbook. But there is such thing as a gas law that actually involves all three of the aspects or elements. But of course, I guess for Form 4, we'll just keep it simple. Okay, but what's really important is, besides learning learning how to use the different formulas, what's even more important, like I said earlier, and like I'll keep saying, what's more important is for you to understand what is the relationship between these three things. So you should be able to answer, like, if I increase the temperature, what would happen to the volume, right? Or if I increase the volume, what happens to the pressure? So you need to know and be able to understand and answer that, because that's what the gas laws are all about. The relationships between the different factors, or the different the different factors of gas. Okay, so that's basically everything for today's lesson. So before I give you, still have a few more minutes left. Is there any questions, or is there anything that you need some further clarification on? Yes. What is it, Emmanuel? Does this apply only to gas molecules? Well, the topic is called gas laws. So, we are dealing with gas molecules. And when I say gas, I don't mean gas as in like gas minyak. All right, remember, gas as in any type of gas. So it could be oxygen, it could be hydrogen, it could be steam. Right, there are different types of gas molecules. But yes, so all these laws are. Oh, we only use this for uh, gas molecules. We don't use this when we're calculating, or at least for this chapter, we won't be using this for liquids or solids. Solids and liquids have their own set of rules that we could learn probably at another time. Yes, thank you. Good question. Any other questions? So we have finally done, well, we are done now with chapter 4, which means after the break, we'll still have another 2 chapters to finish up. So next week you'll be having a break, and then after that, uh, calculating the pressure of the ocean. Okay, no. If you're gonna calculate the pressure of the ocean, you mean water pressure? Remember, water pressure has a different there's a different formula of calculating water pressure. Actually, that will be something you'll be studying in Form 5, water pressure. But actually, you did learn also a little bit about water pressure in Form 2. For liquids, water pressure, and this is a little bit of advanced information, but there's nothing wrong with that. So for water pressure depends on how much water, or not just water, but any type of liquid, depends on how much liquid you have above you. Because the pressure comes from the weight of the liquid above you. Because remember, water has weight, or liquid has weight. So when you're going deeper and deeper and down in a liquid, what happens is that all the liquid above you is applying pressure down on you. So the deeper you go, this is a very basic explanation. The deeper you go, the higher the pressure increases. Now, if you want to calculate it specifically, then you need to know the density of the liquid and, of course, exactly how deep, right? So that's just a very short explanation. You learn that you'll definitely that's chapter chapter 2 or chapter 3 in form 5. So you'll definitely learn that next year. That's also an interesting one. So you'll be learning about that. But for gas laws, we'll only be talking about these will only be dealing with gas. Okay, good questions. Yes, I like the way that you guys are. I like the way that you're thinking about how you can apply this, how you might apply these things into other situations, right? Even though it wasn't 100% accurate, but just thinking about it's a good way to think about these things. That's that. The idea of physics is that you are always thinking, how do I apply this knowledge? How do I apply these formulas into real life situations? Because a lot of the questions in the test are exactly that. They'll be asking you, okay, here's a machine. How can we use the principles of physics to improve this machine? Or here's a situation. Predict what will happen based on the physics formulas that you have already learned. So it's a very good way of thinking. Even if you make a mistake, that's okay. You can always learn from your mistakes. All right, so I was going to ask you to finish formative practice 4.4 today. Um, you can still do that if you can finish it by today and submit it by today. That'll be good. If you submit it by today, then I'll try to return it. No, not try. I'll make sure to return it by today. That's if you submit it by today. And for the rest of the week, because you are having a break after this next week, and this will be assignment over the break, which is to finish up the performance evaluation in your textbook, which is page 148 all the way to page 168. So that will be covering all the different formulas in chapter 4, all the different things that you have studied in chapter 4. So that will be your work for today and also for the coming week. So formative practice 4.4. If you can finish that today, I will return it by today. I know I haven't been 100%, I haven't been 100% good with returning your work, but this one, I promise if you pass it today, I'll return it today. And over the break, meaning to say you have more than a week to finish it, go ahead and do performance evaluation page 165 to 168. Okay, so that's basically it for chapter 4. So we have 2 more chapters to finish up after this, which means we have basically probably 4 to 6 weeks to finish everything. Then you'll have your final exam. So we do not have a whole lot of time. So